Mark Warner. I'm a local here actually, but I'll be around for the 6 months of the workshop as well. It gives me great pleasure to start this afternoon's session. Some people are still leaking in here. And while they're doing so, our first speaker this afternoon is Dr. Canevari. He's going to talk to us about the design of effective bulk potentials. Many thanks.
Thank you very much. I'm very happy to be here. I'd like today to talk about some results, some joint work with Arghir Zarnescu, one of the organizers of this workshop. We are both in BCAM in Bilbao, the Basque Center for Applied Mathematics. And the topic, or the physical motivation for our work, is a study of colloidal nematics. So what are colloidal nematics? Well, we have nematic liquid crystals, this phase of matter, this state of matter some materials can be found in, a phase of matter where the molecules do not have positional order, they are uniformly distributed in space, but they do have long-range orientational order, meaning that molecules that are even quite far apart in terms of molecular length scale, they are still they're still preferring to orient along the same direction. And as a result, you have preferred directions and therefore anisotropic optical properties. So we have this fluid, really, with anisotropic optical properties. And what we do is that we put some some inclusions, some particles into them. Many small particles, small meaning perhaps micron size or less, so actually very large compared to the molecular length scale, but still small compared to the size of the domain. And the result is the colloidal nematic. So that's a composite material. And the interest in this colloidal nematics is that the properties of this composite material may be even quite different compared with the properties of the nematic liquid crystal host alone. Why is it so? Well, for instance, you may choose to put inclusions that carry a magnetic dipole. Then you would have a ferrofluid or so. But not necessarily. You may also put inclusions that do not carry any dipole, any magnetic or electric dipole, and this is what I'd like to talk about today. And if you do so, well, still you see different properties. Still, the presence of inclusions modify the behavior of the material, and that's because even though there aren't dipoles, the inclusions still have a boundary. They have a surface. There will be an interaction between the particle and the liquid crystal molecules, an interaction that takes place around the surface. In fact, you may even treat the surface of your particles so to induce preferred directions of molecular alignment. For instance, the molecules may prefer to stay aligned tangentially to the surface of the particle, or perhaps in the normal direction. And this anchoring, of course, modifies the arrangement of the liquid crystal molecule. As a result of this anchoring, you might see defects, topological defects. This is because the anchoring, let's say, activates somehow, activates some set some topological obstructions, and therefore topological constraints, and you see topological defects. And there are several works on this field, topological defects induced by the presence of inclusions. There are works from the point of view of, well, experimental works, but also, I would say, topological ones. You could classify in a topological way the type of defects you see, points or maybe loops, even exotic shapes, linked loops or knotted ones. There are many numerical and computational results, and there are a few, perhaps less, at least that I'm aware of, but a few works from the point of view of analysis of variational models. Now I put here just a few references and reviews on the topic, but I apologize because I certainly missed many important references. That's really a huge field. This is not, however, what I would like to discuss today. I would not like to talk about defects and topology, because that's not the only way the particles modify the properties of the material. Also, some macroscopical properties or collective properties are modified by the presence of the particle. For instance, the phase transition temperature may change in the composite material, in the colloidal nematic, as opposed to the, let's say, pure nematic, the host. And that goes in the direction of this workshop and in the direction of this thematic semester, really. So the design of new materials, because we may imagine and perhaps invent a way, or hope to, modify, to tune the properties, the effective properties of the material by placing suitable inclusions into your nematic liquid crystals and tune in a suitable way the anchoring of these inclusions. This effect, this modification of the collective properties of the material induced by the presence of the inclusion is present already in the so-called dilute regime. And when I say dilute regime, I mean that the typical size of the inclusion is small compared to the typical separation distance. So what I would like to do today is to discuss about this effect, this modification of the effective properties of the materials induced by the presence of inclusions, and to do that in the dilute regime by studying a mathematical problem. A variational continuum model, it's based on the Landau-de Gennes theory, and by studying a homogenization problem. And I will explain in a moment what I mean by that. Let me just mention before that there are already in the mathematical and physical literature homogenization results about this kind of setting. Perhaps there are results in the that have been obtained at the context of Ginzburg-Landau theory or Ericsson theory. And as I said, what we're doing today is rather in the Landau-de Gennes theory. We had already an introduction to the Landau-de Gennes formalism in the lecture this morning by Jonathan Robinson. I'm grateful to him. And we will be interested in the role played in the mathematical analysis by the choice of the surface anchoring. That will be really the crucial parameter for us. So, before I go further, let me introduce the domain I'm working on. We have, let's say, a bounded smooth domain omega in our free, that's the container for our material. And we have a dimensionless parameter epsilon. So epsilon is dimensionless, and in fact all the model has been rescaled already as I write it down. So epsilon should be understood as a ratio of two lengths, and it's defined in such a way that the domain omega, so the rescaled domain, really has size 1, and epsilon is the typical separation distance between the inclusions. We are considering a continuum theory, and we're looking at equilibrium configuration. Everything is at rest, and the position of the inclusions, we assume that it is given for the moment. So the inclusions are represented by this white set. They are effectively holes in our domain. I call that curly P epsilon. It's a union of several particles, of several inclusions. All the inclusions are identical to each other. They are all rescaled copies of a single reference particle, which I denote curly P. How are they distributed in the domain? Well, let's say, well, they need to be uniformly distributed, or at least we would consider uniformly distributed particles in this talk. And let's say, even for simplicity, that they are periodically arranged. They sit on the vertices of a grid of size epsilon, of a square grid, say, or small perturbations of such an arrangement. How about the alignment? Sorry, I forgot to say that the shape, it's actually the shape, so the set P could be a sphere, they could be cylinders or ellipsoid, quite a general convex and compact set, in fact. And so, because they are not necessarily spheres, we do need to specify their orientations. And again, for simplicity in this talk, let's say that they are all parallel to each other, even though you need not to work with such a setting. They may be slowly varying, for instance. Sorry. And how about the size of the inclusions? That's a crucial parameter. The inclusions have size epsilon to the power alpha. And we assume that the parameter alpha is larger than 1. That means that the inclusions epsilon to the power alpha is small compared to epsilon. And so epsilon is the typical distance between molecules, so we are indeed in the dilute regime. In fact, there's some here. In fact, our parameter alpha will not only be bounded from below, is it okay if I write here? Okay. Will not only be bounded from below, but also from above. Alpha is between 1 and 3/2, and physically that corresponds to a situation where the total volume occupied by the inclusions is going to 0 as epsilon goes to 0, so it's small, but the total surface area is large. It's going to infinity as epsilon tends to 0. So this is our set of inclusions, and then we have omega epsilon, which is the container omega minus the inclusions. So this is the space which is effectively occupied by the liquid crystal material. It's the blue region. Now, our model, as I said, we are working in a Landau-de Gennes setting, so the order parameter is a set of matrices, as we saw in this morning talk by Jonathan Robbins. It's a set of 3x3 real symmetric matrices with trace equal to 0. Every local configuration for the material, for the nematic liquid crystal, is represented by such a matrix. And therefore, the configuration of the material will be a map from omega epsilon to this space of Q tensors. This space of real 3x3 symmetric and traceless matrices, which are defined as second order moments of the probability distribution, of the molecular probability distribution. And given such a description, we can consider a free energy functional. Perhaps I write it here so that it stands. Which consists of several terms. So there will be a bulk potential. That's a polynomial in Q, and that's exactly the same as this morning. It's a quartic polynomial in the scalar invariance of Q by framing difference, and as the trace is equal to 0, we are left with trace of Q square and trace of Q cube. We have these coefficients A, B, and C depending on the material, and A also depends on the temperature. So the dependence on the phase transition temperature is hidden in the coefficient A. This is for the bulk term, which is an integral over the volume. But we also have an elastic term depending on the gradient. And this will be a quadratic polynomial in the gradient, so there will be three elastic constants, L1, L2, and L3, that are constrained to satisfy some inequalities, so that the elastic energy density overall is a convex function, and it is bounded from below and above by the gradient square. It is comparable with the gradient square, and that's required for the mathematical analysis. And finally, there's a surface term. There's an integral over the boundary of the particles. That should represent the anchoring effect of the particles. There's an energy density which a priori will depend on Q and also on Ni, the normal. Ni is the normal to the particle. For the moment, we will not specify it. Sorry. And as we said before, in this regime of parameters, the total area, total surface area of the inclusions is very large. It's going to infinity as epsilon tends to 0. So in order to compensate that, we choose the scaling in such a way to introduce a parameter here, which is small, epsilon to the 3 minus 2 alpha. So overall, when you look at this term, you should expect, you would expect, or that this coefficient, this small coefficient, compensate for the large surface area. And overall, we could perhaps expect that the contribution of the surface term is comparable, is of the same order of the contribution of the volume integral. Now, this is our free energy functional. We still have, again, to choose choose in a reasonable way our Fs. It's not given for the moment, but and we are interested in the limit as epsilon tends to 0. This is what I mean by the homogenization problem, or the homogenization limit. This limit is the limit where the particle gets small compared to the size of the domain, but they also get closer to each other. And what we would like to do is hopefully to study the limit of this free energy functional, because that should be a sort of effective free energy, which we hope would give us some effective properties of the material, of the composite material, some homogenized properties of the composite material. Now suppose we are given a fixed domain, omega, but also a fixed material, a fixed liquid crystal material with some coefficients A, B, and C that are given to us. And we would like to obtain a composite material with other coefficients A prime, B prime, and C prime. So the question now is, can we choose the inclusions in such a way, and in particular, can we choose the anchoring in such a way that starting from our given material with parameters A, B, and C, in the limit as epsilon tends to 0, we obtain a functional such as this one, with pre-assigned coefficients A prime, B prime, and C prime. This is the design problem. If you prefer, it's a control problem, where we are given both the initial parameters A, B, and C, and the parameters A prime, B prime, C prime that need to be there in the limit. And what we want to do is to choose, in a suitable way, the surface anchoring energy density, Fs, so that this on top converges to that in the limit as epsilon tends to 0. So this is the question we ask ourselves in this talk. And well, before we study the question, let us look a little bit of what are the possibilities are for the surface energy anchoring, the surface energy density. Such an energy density should be invariant by rotations, because that's frame indifference. It should also be invariant by orientation, meaning that if I have an interface, it shouldn't matter whether the liquid crystal is on the right side or on the left side. Mathematically, you can combine both the requirements, so invariance with respect to rotation and invariant with respect to the choice of the orientation, into this requirement, which is invariance with respect to orthogonal matrices. So given any orthogonal matrix, a rotation, but also a reflection or combination of both, you let the rotation matrix act both on the Q tensor and on the normal. And this action shouldn't affect the energy density. The energy density should be invariant. Now we could list some possible expressions that do satisfy this symmetry requirement. For instance, the scalar invariance of Q are fine. They do not depend on the moment, on the normal, but they do satisfy that condition. Or also you could came out with this, for instance, Q ni dot ni. Or perhaps Q squared ni dot ni. And by the way, because Q is symmetric, it's really difficult to see here, probably. This is the same as the mod square of the product, Q ni. And of course, any function of this quantity would also do. Now, in fact, surface energy density of this type that do satisfy this requirement can be written as a function of these quantities have been proposed in several places in the literature. It turns out that this is the only possibility. So if you give me a surface energy density that does satisfy this requirement, by linear algebra it turns out that it must be a function of this invariance. So at least we know what should be, from the point of view of physical symmetries, the admissible energy densities. And now let us do some heuristic computation. Let's suppose for simplicity that inclusions are spheres and that our energy density is given by the expression on top, q squared ni dot ni. What happens? I want to estimate the surface energy integral. Of course, I decompose the integral as a sum of integrals over each single inclusion. And then, because the inclusions have radius epsilon to the power alpha, so it's a small quantity, it should be fine to approximate the value of actually q squared, on the boundary of the inclusions of a single given fixed inclusion by the value that q squared takes at the center of the inclusion. But if I do that, the value of q squared as a center is a constant. I've pull it out of the integral. I am left with a geometric integral only. I can make a change of variables so to reduce to a unit ball. By doing the change of variable, there's a Jacobian factor, and so I will kill this epsilon to the minus 2 alpha. And now I'm left with this. I have a sum q squared at the center contracted with an integral. This integral is a matrix. By symmetry reasons, because we are working with spheres, it will be a multiple of the identity, and therefore what I have here is nothing but the trace of q squared evaluated at the center of that E inclusion, summed over E, and that will be multiplied by a parameter that scales by epsilon to the power 3. So what I'm doing is, if you wish, a numerical approximation of a volume integral. So that surface energy term can be approximated in principle in the limit as epsilon tends to 0 by a volume integral. That seems nice because it means that by choosing a surface energy like this one, we should be able to change the parameter A in the bulk energy, the quadratic parameter. And the game we played with a quadratic term, we could also play for the cubic of order 4 term, I'm sorry. Now, this is just an example. Of course, there could be other expressions and perhaps more physically significant ones, but the point is, it seems that the design problem has a positive answer. By putting this term into the surface energy, we can change more or less at will the bulk part of the energy in the limit, except that it's not quite that simple. Some care needs to be taken. Suppose, for instance, that we do not want to modify the parameter A, the quadratic one, not even the cubic one, but we do want to modify the quartic one, the C, and we want to make it smaller. In order to do that, we should choose as a surface energy a polynomial or a function of degree 4, and because we want to make it smaller, we should have a negative coefficient in front of the surface energy. So that surface energy would be of degree 4 in Q, of quartic growth, and of negative sign. And this makes the analysis quite difficult, actually. It complicates a lot, the mathematical analysis, because, well, I can skip this probably for the moment, because even before we consider the limit as epsilon tends to 0, in order to analyze our problem, we must study the problem for fixed epsilon and make sure that perhaps it has minimizers or reasonable solution. In order to have minimizers, we would like to have a functional that is coercive, so it satisfies suitable lower bounds, And we will need to take limits, we would need that the limit of a minimizer sequence is a minimizer, so we need some compatibility of the functional with the fact of taking limits. Some continuity, or rather weak, lower semi-continuity property. Now, if I choose my surface energy density to be a function of degree 4, of growth 4 in Q, and a negative one, then both these conditions are lost. This functional, if I choose f as, for instance, of this form, quartic and negative, the functional will not be coercive anymore. In fact, it will be unbounded from below. So there cannot be global minimizers. And it will not be lower semi-continuous either. That means you can construct sequences of configurations for fixed epsilon, sequences of configurations that perhaps are very localized in a portion of your domain, near one inclusion, for instance, and otherwise converge, say, to 0 or to some other constant state, perhaps, outside that very localized region. The energy, so in particular, the limit is 0, so the energy of the limit is also 0, but the energy of this sequence do not converges to 0 or is not positive. It doesn't have a positive and non-negative limit. The energies stay negative, which means in the limit we are actually gaining energy. And this is quite a bad situation from the point of view of the calculus of variation. There's not much in principle you could do if such a lack of lower semi-continuity is met. And the problem is that when you have something which has quartic growth in the surface energy, well, the mathematical rationale, if you wish, behind this is that the Sobolev embedding of your trace space into L4 is continuous, but it is not compact. And that means that in the presence of a surface energy of degree 4, this cannot be considered as a lower order perturbation. So everything seems lost, but in fact, not really. Well, there's a way to work around, and perhaps due to time constraints I will skip something. The remedy, one possible way to manage this problem from the point of view of the mathematical analysis is to consider an additional gradient bound. We suppose from the beginning that we are looking at maps that have a bounded elastic energy. The integral of the gradient square of my configuration is less than some given constant, arbitrary but fixed, m. And this is fine. We are only looking on a bounded subset of the energy space, but it's quite fine if we are interested, for instance, in local minimizers of a problem. So critical point that minimize the energy only in a given ball, in a given bounded region of the energy space. Now, if we do restrict to configurations that have this gradient bound, and if we take epsilon small enough, and the smallness of epsilon will need to depend on the gradient bound, then we are able to restore the lower semi-continuity. Then we have a statement that says whenever a sequence of configuration converges in a suitable topology to something, the energy of the limit will be controlled by the limit of the energies. And this is what we need in order to study the problem from the point of view of the calculus of variation. What is behind this property, this fact, is that even though the surface energy has perhaps the wrong sign, and it is not a lower order term, well, it is not a lower order term, so let us couple with the other higher order term, which is the elastic energy. This elastic energy has the right sign. It is a convex function. And the coefficient, which is here, is small. because we have chosen alpha less than 3/2. So this good sign here, the good sign here can compensate for the disturbing effect coming from the surface. By the way, the restriction on alpha is not completely artificial because it's sharp. If you were to take an alpha greater than this, then you would, there would not be uniform energy bounds, even on bounded subset of the energy space. There's no hope really to study the problem, the limit. And finally, once we have made sure that the properties, the mathematical properties of a problem are good for fixed epsilon, we can pass to the limit. We could study the limit and formulate asymptotical results in a general framework, but perhaps because of time restrictions, it's better to consider already the application to the particular Landau-de Gennes framework we are interested in. So again, we are starting with a given Landau-de Gennes free energy with fixed coefficients A, B, and C. And we would like to obtain in the limit this other Landau-de Gennes energy with, again, pre-assigned parameters A prime, B prime, and C prime. In order to do that, we need to choose carefully the surface energy. And the way to choose carefully the surface energy is dictated by the formal computations we saw before. We will need to introduce a quartic term in a quadratic term in the energy density in order to modify this term. For instance, this one, but you could cook up other terms, and there's a recipe for that. A cubic term to modify the parameter B, and a quartic term to modify the parameter C. And now, because of the analysis in the slides before, I'm not really worried if this C prime is less than C or C prime is bigger than C. Now the statement is, suppose that we have an isolated local minimizer for this limit function. So it's a stable solution of the homogenized, or a stable critical point for the effective, if you wish, free energy. Local and isolated are referred to the topology of the energy space, so H1. But suppose we have such a isolated locally stable state for this functional. Then, for epsilon small enough, there exists a local minimizer for the functional above. So a local minimizer, a locally stable solution for the original problem, in such a way that in the limit as epsilon tends to 0, the local minimizer for the problem above converges to the local minimizer for the problem below. And that is our homogenization results, which in a way justify how this effective free energy is a reasonable approximation of the free energy above. And there's again a numerical recipe which involves just computing some integrals to obtain at least mathematical expressions of energy, surface energies, so to pass from the functional above to the functional below. As again a particular case, we could consider, for instance, the Rapini-Popular surface anchoring. The Rapini-Popular surface anchoring is given by that expression above, so it's proportional to the trace of Q minus the trace of some other tensor, which is defined in terms of the normal to the surface. In particular, let us assume that A prime is bigger than A, so that that coefficient over there is positive. And then the surface energy, this type of anchoring, will prefer normal alignment to the boundary of the particle. Well, in that case, if you choose this particular free energy, you are able to pass from that functional above to this functional below with B prime equal to B, C prime equal to C, So you are changing the value of A. And changing the value of A can be seen because A depends on the transition temperature. Increasing the value of A can be interpreted physically as lowering the phase transition temperature. You can even estimate numerically in terms of order of magnitude the gain or loss in terms of phase transition temperature from the given phase transition temperature to the effective one induced by the presence of colloids, and it's effectively something of order 1. If you choose, for instance, an anchoring with that strength, so actually it's quite a strong one, and perhaps even quite spaced, I would say, inclusions, so even more than micromagnetic spacing. Of course, you could do, you could imagine to consider other types of anchoring. So to modify not only the phase transition temperature, but also the other parameters in the free energy. So that concludes, I think, what I would like to say, and I thank you very much for your attention.
Thank you for a very clear talk and a very timely talk. It's right on time. Does anybody have questions? Yes.
Could you please say again why you're able to replace the Q tensor at the surface of the particle with the Q tensor somehow in the center?
Well, that's a formal heuristic computation. Let's say heuristically, I have no better explanation than the surface, the inclusions of the particle are small, so doesn't. The point is that after this heuristic computation, which is useful because it tells you how to choose the right expression for the surface energy, you can indeed prove a convergence result. And
so I must say I was sort of concerned about that myself, because that's the one place in the domain that's excluded, or one of several places that's excluded. So you're saying that the order parameter, you look at some sort of continuation or extrapolation to that point that's excluded?
Yes, in a way, yes, in a way. That's also an effect of the, an important parameter at least here is the fact that we are working in the dilute regime, meaning the particles are small compared to the typical separation distance. If the particle were not that small compared to the separation distance, not only there would be effects in terms of the bulk energy, but you would also see effects in terms of the elastic energy, which perhaps goes in the directions you are, if I'm not sure whether I understood your concern, but the point is,
I think it was Daniel's concern as well, that you're taking the value at a point which is excluded from the domain. Yeah.
In a way, it doesn't have to be the center, sorry. It might be a fixed point. I mean, it was just heuristic anyway. The point is, in this particular scaling and framework, because we have chosen the scaling of the surface energy in this way, and because we are in the dilute limit, it is, in fact, a posteriori, because of the convergence result, justified to approximate what happens on all the surface of the particle by taking just a constant, which I wrote as the value on the center, sorry, but you may see that it's a value at any nearby point.
Other questions? Yes.
Something that means your theorem is phrased for spheres?
So, well, the theorem, the general convergence theorem can be for any convex compact inclusion, satisfying perhaps some kind of weak conditions. In particular, the example, this expression, this is for spheres. For ellipsoid, for instance, you would need to choose another expression here. and that would be more difficult to compute explicitly.
So something with traces or whatever. Yeah. But it is reconstructible somehow.
It is, in fact, well, I skipped that because I thought, but the formula is over there. Given an fs, you can define by computing an integral, which is that one, the homogenized, let's say the effective addition to the bulk potential due to the surface energy. And then the problem is, can I choose fs in such a way that that parametric integral is equal to what I want it to be? For spheres, it's easy. For ellipsoid, it's perhaps doable, but it's just a bit more nasty. Right.
Dario.
So in your final example, you have an expression which contains w squared, isn't it? Does that mean that
Sorry,
the Rapini, no, at the very end you had probably that one. Yeah, you have the anchoring Rapini coefficient w
Yes.
squared.
Y squared?
Perhaps it's by bad eyes, but I thought
No, sorry, it's ws for surface. Sorry, it's just bad notation, perhaps.
No, it's my bad eyes. Because then I was wondering if the shift in the transition was indifferent on the sign of the anchoring, of course.
No, it's
well,
W super S.
But in this case it is. Instead it can go lowering or increasing.
Depending on the sign.
Which is
Depending on the sign.
Yeah, which is
Yes.
what I expected.
Yes, exactly. Yes, let's say for convenience, or just because for this type of anchoring in particular, perhaps because of I was more used to expression with the positive coefficient, and to have a positive coefficient that corresponds to have a larger A prime. But of course, if you are willing to take negative, then you go in the other way, yes.
In the case that it is slippery, it's just zero.
What do you mean slippery, sorry?
There is no interaction, it just occupies volume. You have no shift. Is that
Okay, yes, I think so, yes. In that case, there's no...
Can I ask a quick question, and that is, as an outsider, you displayed these wonderful defects that you have normally on the surface or coming from the surface, and then you disposed of them. And why can you just sort of remove them?
Well, let's say the point is, I think that the strength of the anchoring is another, as well as, again, the fact that we are working in the dilute regime. They are very crucial parameter from this point of view. Perhaps if we were to choose a different scaling coefficient here we have chosen the scaling in such a way that in dimensionless units you have this small coefficient here. But if you were to choose a larger coefficient, then really defects would, you could not get rid of them. They would be there because it would be a very strong penalization.
Well, look, you've come in very nicely in time, and we can discuss further later. I'd like to thank our speaker.
Thank you.